In this video, we're going to take a look at finding volume by a method called cylindrical shells. So if we take a look at a function f of x, such as what we have right here, and we create a rectangle underneath that, which would be this rectangle right here. Now, in the washer method that we used before, we would have revolved that rectangle around the x-axis, creating a disk. And that gives us the name of the disk method. But instead of revolving around the x-axis, we are actually going to revolve it around the y-axis. So when we take this little rectangle here and rotate it around the y-axis, we end up with what is called a cylindrical shell. So you should be able to visualize that. The thickness of the rectangle would be the thickness of the cylindrical shell. The radius of the cylindrical shell, the distance from the axis of rotation to the actual rectangle itself, well, that distance here is a distance on the x-axis. And then, of course, the height of the cylindrical shell is simply the function value, f of x, right? Because the function value goes from the x-axis to the actual function. So the height of the rectangle becomes the height of the cylindrical shell. The radius of the cylindrical shell is x. The distance from the y-axis to the rectangle is an x value. And we are rotating it around the y-axis. All right, so if we take a whole bunch of little rectangles, like we always do, take a whole bunch of rectangles and rotate all of these rectangles around the y-axis, then what we're going to have is a whole bunch of cylindrical shells like we have in this diagram here. Now, the interesting thing about that is we can find the volume of each cylindrical shell very, very easily. And so we'll take a look at how we do that now. To find the volume of any particular cylindrical shell, we can split it open. Okay, just cut it right straight down and lie it open. And when you do that, you formed a rectangle. And so the volume of any rectangle, the volume is basically the length times the width times the height. And so we'll call this distance the thickness of the rectangle is delta x, so we'll call that delta x. The height of the rectangle is f of x. And then we have the length of the rectangle. The length of the rectangle says 2 pi x. Now, where does that come from? Where that comes from is 2 pi x is equal to the circumference of this cylinder. Okay, the circumference is equal to diameter times pi, which is equal to, and diameter is 2 times the radius times pi. So the circumference is 2 times r times pi. And so remember what I said before, that the radius is an x value. Sorry, I've got a little cough. So we can replace 2 pi r with 2 x times pi. And so that's what we have here, 2 pi x. All right, so essentially the volume of the cylindrical shell is going to be the function value is the function value. Again, that gives us the height times 2 pi x, which gives us the length, times delta x, which is the thickness, or we'll call it the width, whichever you want to call it. So there's our 3 dimensions. All right, so hopefully that makes sense. Well, we know we have a whole bunch of cylindrical shells, right? We have all of these cylindrical shells in here. And we can do what we've done so many times before, is we can create a Riemann sum. We can sum up all of the volumes of these cylindrical shells. And when we do that, we'll have an approximation of the volume. Well, the next step, as always, is to take the limit as the number of shells approaches infinity. And as the number of shells, n, approaches infinity of the Riemann sum, we end up with an integral. That integral is the integral from a to b of 2 pi x f of x dx. Now, it helps to have an idea as to where these formulas are coming from, so that when you're looking at the formula and you're looking at a problem, you can figure out all of the various pieces. So just looking at this formula, let's dissect it. 2 pi is a constant. The 2 pi comes from the length. The x is the radius. 2 pi x altogether was the radius. But remember, 2 pi is just a constant, so we could put 2 pi out in front times the integral of x f of x dx, where x represents the radius, the function value f of x represents the height of the rectangle, times dx. So what we really need to do is we're going to have an integral 2 pi times the integral from a to b of some value x, which is the radius, times some f of x, which is going to be the height of the rectangle, times dx. Okay, so just remember, you have to have the height and the radius in here. That is what composes your integral. All right, and so that's all summarized in this rule. Let's do a problem. So in this particular problem, as always, we want to draw a picture. If you need to, go to Desmos. This is a pretty simple one to graph. It's just 1 over x. And it is being bound between 1 and 3, so we're given all the necessary information we know. We're going from 1 to 3. Now, what I like to do when I'm doing cylindrical shells, I always do this. I encourage you to do it too. I draw myself a little rectangle in here, just like I had there. Now I'm coloring it in green. There's my rectangle. And I'm rotating that around the y-axis. So just like in the example problem that we did. I want you to notice one thing. In cylindrical shell problems, the height of the rectangle is always parallel to the axis of rotation. That's just the opposite of when we were doing the disc in the washer method. In the disc in the washer method, we would have rotated this green rectangle over the x-axis, and it would have been perpendicular to the axis of rotation. Now it is parallel to the axis of rotation. So it's just kind of an important thing to remember. It's kind of a handy thing to remember. All right, when I'm setting up these problems, there's 3 things I like to find. First of all, what are my bounds? Well, again, the bounds were given to me, 1 and 3. And then remember, the formula has a radius and it has a height in it. So the formula, I'll write it down here, the volume is equal to 2 pi times the integral from a to b of x f of x dx. And again, x is a radius, f of x is a height. So let's write down, what is our radius? Well, the radius of this rectangle right here, my green rectangle, is the distance from the y-axis to that rectangle. So that's a distance of x. Now, it's not always going to be just plain x, as you'll see in some of the later examples. The function value is the height. Well, what is the height of the rectangle? Well, the height of the rectangle, since the top of the rectangle intersects the function, it is the function value. So the function value is the height of the rectangle. And so we have all the components that we need. We can just put them right into our formula. Volume is equal to the integral from 1 to 3 of 2 pi x, the radius, 1 over x, the height, times dx. Simplifying that a little bit, we get this. And so that's pretty easy to integrate. We end up with 2 pi x from 3 to 1. Our final volume is 4 pi. So this is a nice simple example, but it helps to drive home the important points, which is make sure that you find the bounds, the radius, the height, because you're going to need those in your formula. Draw a little rectangle in here and make sure that you know that that rectangle is going to be parallel to the axis of rotation, the height of the rectangle, that is. And then just put everything into your integral. Next example. Again, you probably want to go to Desmos, graph these two functions in Desmos, let Desmos do all the work to figure out what the points of intersection is, but one point of intersection is here at 2, and the other one is at 0. All right, so we want to find the volume generated by rotating this region. So remember, I'm not drawing the actual volume. I can't draw volume very well in here. All I'm doing is drawing a two-dimensional cross-section of the area that is being rotated, and we're rotating around the y-axis again. So here's my rectangle. I'm drawing in my vertical rectangle. It's being rotated around the y-axis. It's parallel to the y-axis. So what do I need? I need my bounds. Bounds are from 0 to 2. That comes directly from the graph. The radius is, once again, the radius is going to be the distance from the y-axis to my rectangle, which is an x value. And then the height of the rectangle. Well, the height of the rectangle is going to be a little trickier because we actually have to take the difference in the function values. The top of the rectangle is right up here at 18x minus 6x squared. The bottom of the rectangle is down here at the other function, 3x squared. So to find the height of that rectangle, we subtract the two functions. And so that's what I did here and simplified it to get that. And we've done that in previous lessons. But we have everything that we need to put together the integration problem. So we have the 2 pi, we have our radius, we have our height, times dx. From here, it's just simplifying, integrating, and voila, you get your final answer, 24 pi. And as always, you can check these in Desmos by converting to decimals. And one more. Exercise 3. Use the method of cylindrical shells to find the volume generated by rotating the region bounded by the curves 3e to the negative x squared, y equals 0, x equals 0, and x equals 1. So graph the function. Use Desmos if you need to. Then draw yourself a little rectangle inside the region that you are rotating. And so we are rotating about the y-axis. So I'm rotating about the y-axis. And again, my rectangle is parallel to the y-axis. And so let's figure out our parameters. Bounds are from 0 to 1. Boom. The radius, once again, is the distance from the y-axis to the rectangle, x. The height is the function. So that's pretty straightforward. Putting it all together in your integration problem, you end up with the integral from 0 to 1 of 2 pi x times 3e to the negative x squared. That's kind of sloppy, so you can multiply the 2 and the 3 together. But in order to actually do some integrating, we're going to have to do something we haven't done in a while. You're going to have to do some u substitution. So I think this is the first u substitution that we've seen in a while. You're going to be seeing some more of them. So if you need to, go back and review from Calc 1 on how to do u substitution. The Organic Chemistry Tutor has some really good videos. There's lots of really good videos out there on that. But you basically start by letting u be equal to negative x squared. Take the derivative of both sides. The derivative of u is du. The derivative of negative x squared is negative 2x dx. And then solve that for dx. And when you solve that for dx, you get dx is equal to du over negative 2x. And so you remember in U substitution, we substitute in anything with an x with a u. So we let the negative x squared be equal to u. So I substitute that in there. Let's do that in a different color. Substituted the negative x squared was my u. And then I took out the dx and put in du over negative 2x. Well, now the x's down here cancel out. That 2 cancels with that 2, but I still have the negative sign. That comes out front here. And then the 3 comes out front. The pi comes out front. So we have a negative 3 pi times the integral of e to the u du. And the antiderivative of an exponential is the exponential. So the derivative of e to the u is e to the u. Substituting back in the x's, we end up with negative 3 pi e to the negative x squared, evaluated from 1 to 0. And you get, this is about as simplified as I could get it. And I think that's pretty much what WebAssign is going to want you to have. 3 pi times the quantity 1 minus 1 over e. Okay, well, that's it for this video. That should get you started on using the cylindrical shells method. Make sure that you understand these 3 problems. Make sure that you can justify and you understand all of the parts of what you're doing before you go on and look at the next video and try to do the next problems. All right, see you then.